Welcome back to the Deep Dive.
Great to be here.
Today we're diving into something pretty fundamental, programming languages.
Yeah, why on earth are there so many? It seems kind of messy from the outside.
Exactly. Why so many ways to tell a computer what to do. And, with AI booming, could coding itself be changing?
Maybe even heading towards using, well, just plain English. It's a big question.
It really is. And it's a landscape that looks fragmented, but as you said, there are usually solid reasons underneath.
Absolutely. And our sources for this deep dive really help us unpack those reasons, I think.
Yeah, we pulled together some interesting bits for this. We've got excerpts from a Bartleby article looking at the idea of a single universal language,
Right.
pros and cons,
Okay.
a really good Reddit thread, the ELI 5 style, explain like I'm 5, why not just one language?
Always useful for getting to the core idea.
Totally. Then some more foundational stuff from programming language design concepts.
Right. Getting into the weeds a bit.
And this really intriguing Slashdot piece asking, basically, is English the next hot programming language because of AI?
Ooh, okay. That's definitely current.
So our mission really is to weave through these sources, get a handle on why we have this language zoo, and figure out what this AI moment might actually mean for how software gets made.
And the goal is to give you the key takeaways quickly, right? So you feel like you've got the picture without drowning in detail.
Exactly. Let's unpack this. So let's just jump right in with that big question. Why isn't there just one language for everything?
Well, it's fundamental, really. When you look at why different languages were created, you see they're trying to solve different problems. They have different goals baked in from the start.
Right. It's not just people making new ones for fun, though maybe sometimes.
Maybe a little, but mostly it's about purpose. The sources highlight this again and again.
That Reddit thread had a great analogy.
Yeah.
Farms. Yeah, like you wouldn't use a Formula One car to haul bricks.
Definitely not.
Or try towing a boat with a smart car. Different tools for different jobs.
That's a perfect analogy. Some languages, like C, are built for getting really close to the hardware.
Okay, low-level stuff.
Exactly. Managing memory directly. Super fine-grained control. You need that for operating systems, embedded systems, stuff like that.
And then the opposite end.
You've got high-level scripting languages. Think Python. The goal there is speed of development.
Getting things done quickly.
Right.
Yeah.
Automating tasks, gluing systems together. You absolutely don't want to be messing with memory addresses. You want it to be easy and fast to write.
And trying to make one language that's amazing at both.
The sources suggest that usually leads to compromises. It ends up being too complex, maybe not great for either specific use case.
Sort of jack of all trades, master of none.
Kind of, yeah. And think about the kinds of problems we solve with code. It's huge.
Mm-hmm.
You've got, like, heavy-duty physics simulations needing maximum efficiency.
Right.
Then machine vision, movie CGI, massive global networks, cryptography.
These are multi-billion-dollar industries relying on very specific, high-stakes code.
Exactly. They have unique needs that drive language design.
And speaking of specific needs, COBOL came up. That feels ancient.
It does, but banks and big financial institutions still rely on it massively.
Right.
Because it's apparently really good for what it does. Business transactions, accounting, batch processing. The sources say it's verbose, sure, but the code is relatively easy for others to understand and maintain.
Which is critical in a bank, I guess.
Absolutely. And it's still getting updates. I mentioned 2022, 2023 updates. It persists because it's the right tool for that specific job.
Wow. Okay. And then you mentioned scripting languages like PRL and Python.
Yeah, they fill a different niche, often used for shorter programs, quick tasks like glue code, connecting bigger systems written in maybe C++ or Java.
So development speed is more important than raw execution speed for those.
Often, yes. And Python is singled out in one source as, probably the most modern and best designed of that bunch. It's certainly hugely popular.
Okay, so different jobs need different tools. What about the people making the languages? Do their opinions matter?
Oh, massively. The sources bring this up explicitly. There's that old joke, right? Ask two software engineers.
Like a three opinion.
Exactly. Language designers have strong, often differing ideas about what programmers need, what good code looks like, how problems should be solved.
And those opinions become, well, different languages.
Precisely. Each language embodies a certain philosophy or set of trade-offs that its designer believed were important.
And there's history, too. right? A kind of ebb and flow.
Yeah, one source mentioned this cycle. You have early languages like Fortran, literally designed for punch cards, PL1, assembler, COBOL,
The pioneers?
right? But then sometimes languages grow incredibly complex over time. C++ gets called out, uh, rather colorfully.
Let me guess, the psychopath comment.
Huh, that's the one. Too complex to use every nook and cranny unless you are a psychopath. So when a language gets that complex, it creates an opening, a desire for something simpler, cleaner. And the cycle might start again. It's constant evolution.
Okay, that gives us a really good sense of the why. So many factors driving this diversity. To understand how they differ, maybe we should touch on some of those core concepts language designers wrestle with.
Yeah, definitely. Because that's where you see the rubber meet the road, how these different philosophies actually translate into features.
So first up, types, like numbers, text, true, false.
Exactly. How a language handles different kinds of data. Integers, floating point numbers, Boolean values, the basics.
And how does that make languages different?
Well, they differ in what basic types they offer, how you can combine them into more complex types like arrays or records.
Like lists of things or bundles of related data.
Right. And even how those are handled. Like, are array indices zero-based like in Java, or can the programmer choose the range like in Ada? Little details, but they add up.
Okay. And this ties into type systems, right?
Okay.
Static versus dynamic. That sounds important.
It's huge. It's about when the language checks if you're using types correctly.
So static typing.
Static typing, like in C++B, Java, Adases, the checks happen before the program runs, usually when you compile it.
Like proofreading before publishing.
Exactly. It catches type errors early. Before you run it, if you try to add a number to someone's name, for instance.
And dynamic typing.
Dynamic typing, think Python, JavaScript, LISP. The checks happen while the program is running.
Okay. So you might not find the error until it actually happens.
Potentially, yes. Variables don't have fixed types declared up front. The values they hold have types. It offers more flexibility when writing.
Less boilerplate, maybe?
Sometimes, yeah. But the trade-off is that type errors might only show up at runtime, sometimes in unexpected ways. Though the sources note it can be genuinely useful sometimes, like if a function needs to handle different types of input discovered only when it runs.
Interesting trade-off. Flexibility versus early error detection.
That's a good way to sum it up.
What about just the flow of the program, step by step?
Control flow. Yeah, how the program moves from instruction to instruction. Beyond the basic sequence, if then else, loops languages differ in how they handle nonlinear jumps.
Like goto, is that still a thing?
It exists in languages like C, but it's often discouraged because it can make code hard to follow. But languages offer other ways too, like break to exit loops or exceptions for handling errors.
Like Java's throws.
Exactly. These mechanisms allow control to jump around, but managing that complexity, especially when jumping out of nested blocks or functions, is a design challenge.
Okay. And all these different ways of handling data and flow, they feed into bigger picture ideas, right? Paradigms.
Absolutely. Paradigms are like the overarching architectural styles for programming.
Give me some examples.
Well, the most common is probably imperative. That's C, Java, C++, Ada. It's based on commands that change the program's state by updating variables, like giving a recipe.
Do this, then do that.
Pretty much. Then you have object-oriented, or OO, think Smalltalk, C++, Java, C#. It builds on imperative, but organizes code around objects that bundle data and the operations you can perform on that data.
Like modeling real-world things?
Sort of, yeah. Concepts like classes, inheritance, where objects get properties from parent classes are key.
Okay, what else?
Functional programming. This is different. Languages like LISP, ML, Haskell. The focus is on functions that transform data, ideally without side effects like changing variables elsewhere.
More like mathematical functions.
In a way, yes. Haskell is mentioned as a pure functional language that avoids variables and assignments altogether. Some cool features like lazy evaluation come out of this.
And there was one more. Logic.
Yeah, like Prolog. It's based on defining relationships and rules, and the program tries to find solutions through logical inference. Very different mindset.
Wow. Okay, so imperative, OO, functional, logic. Those really sound like fundamentally different ways to think about solving a problem with code.
They absolutely are. And the paradigm heavily influences how a language feels and what it's best suited for.
And one last concept, making code reusable. You mentioned abstraction.
Right. Crucial for handling big projects. Procedural abstraction is the basic idea of packaging code into functions or procedures. You call the function, you don't need to know exactly how it does its job, just what it does.
Hiding the details.
Exactly. And generic abstraction takes it a step further. Think templates in C++ or generics in Ada or Java. It lets you write code, like a list or a sorting function, that can work with different types of data without rewriting it each time.
So you write it once, use it for numbers, text, whatever.
That's the idea. Huge for writing reusable libraries.
Okay, fantastic overview. That really paints a picture of why languages are so different under the hood.
Mm-hmm.
So, bringing it back to the present, what about this idea from Slashdot? Is English, powered by AI, becoming the next programming language?
Yeah, this is where things get, well, really interesting and maybe a bit hyped. So, the idea is that with generative AI tools like GitHub Copilot and others, people can just type prompts in natural language.
In English, say.
Right. Write me a function that does X, and the AI spits out code in Python or JavaScript or whatever.
And some big names are really pushing this idea. Jensen Huang from NVIDIA.
Yeah, he's quoted calling it a miracle of AI, saying it closes the technology divide. His pitch is basically, tell the computer what you want, it'll do it. No need to learn C++ what.
Satya Nadella at Microsoft has said similar things, right?
The argument is that programming isn't just for specialists anymore. Anyone who can clearly describe a problem can potentially create software.
And there was that stat 41% of code on GitHub being AI generated in 2024, according to Stability AI CEO. That sounds huge.
It does. If true, it suggests a massive shift is already happening. Proponents see this democratizing software development.
Okay, that's the optimistic view. Yeah, but the sources also poured some cold water on this, didn't they?
Oh, definitely. There's significant skepticism. A big one is, what about the quality of that generated code? Is it reliable? Is it maintainable?
The usual problems with auto-generated code, maybe.
Yeah.
Hard to understand, hard to fix.
Exactly. That's a historical issue. Plus, practical problems. AI models are trained on past data. They might suggest outdated libraries or security practices from, say, 2013 that are now bad ideas.
Ooh, that's a good point. Training data lag.
Right. Or the AI might just write out complex logic directly instead of using a standard library. That works now, but if that library changes later, your AI-generated code is suddenly broken and hard to update.
Some sources called it later stage tech, hype cycle stuff, comparing it to old do what I mean jokes.
Yeah, basically saying, we've heard promises like this before, be skeptical. There's a strong counterargument that the hardest part of programming isn't writing the syntax.
Yeah.
It's figuring out exactly what the code needs to do. Every little detail, every edge case, that rigorous thinking.
So telling the AI what you want isn't the hard part. Knowing precisely what you want in enough detail for a machine, that's the challenge.
That's the core of the skeptical argument. From that view, prompting AI is just another high-level way to specify instructions, maybe like low-code tools, which we've had for ages. It's not necessarily eliminating the fundamental difficulty.
And can you really describe something super complex like a whole database system just using English prompts?
That seems like a major hurdle right now, based on the sources. Even the proponents, like Huang, admit there's an artistry to prompt engineering.
Meaning you still need skill to talk to the AI effectively.
Right. You need to be precise, clear, iterate on your prompts. It's not just magic, it's a different kind of skill.
So the picture is, AI gives us a new way to interface with code generation using natural language.
Yeah, a potentially powerful one.
But the underlying need for precise problem definition and logical thinking probably doesn't go away. It just looks different.
That feels like a balanced take based on what we read. The syntax barrier might lower, but the thinking challenge remains.
Okay, so given we have all these different languages, good for different things, and now AI adding another layer, how do people build big, complex software today?
Well, one important practice the sources mention is polyglot programming.
Polyglot, meaning multiple languages.
Exactly. It's the idea of using several different programming languages within the same application.
So not just picking one winner for the whole project.
Nope. You might use, say, Java for the main backend logic, Python for some data analysis scripts, JavaScript for the front-end user interface.
Picking the best tool for each specific part of the job.
Precisely. If one language is great for performance-critical calculations, use it there. If another is perfect for quick scripting, use it for that.
And the upside is better results, faster development.
Potentially all of the above. You leverage the strengths of each language. The sources suggest it can lead to a more optimal final product, maybe faster development if teams can specialize, and sometimes even easier maintenance because each piece is built with the most suitable tech.
So it embraces the diversity instead of trying to force one language onto everything.
That's the core idea, yeah.
Wow, okay. This has been a fascinating journey, from why we have COBOL still running banks to maybe coding in English someday.
It really connects a lot of dots, doesn't it?
So summing this up for you, the listener, what are the key things to take away?
Well, first, I'd say that the huge number of languages isn't really a mistake or chaos. It actually reflects the huge variety of problems we solve with computers and the different ways smart people have figured out to tackle them over decades.
Yeah, that diversity has deep roots in purpose and design philosophy.
And understanding those core concepts, types, paradigms, control flow, helps you see why languages are different and why you might pick one over another. It's not just about the surface syntax.
Right, and now AI comes along, offering this new way in using natural language prompts.
Which is exciting. It could lower barriers. But that skepticism is important too.
Yeah, remembering that the real challenge might still be figuring out the problem in excruciating detail, no matter if you're typing Python or prompting an AI.
The precision matters.
So we've gone from punch cards and Fortran through all these different ways of thinking about code, right up to AI potentially writing it from English prompts.
It shows how dynamic the field is. The only constant is change, maybe.
Huh, perhaps. The world of programming languages is so rich because the problems are so diverse.
Definitely.
And AI might genuinely change how we interact with that complexity, using natural language as a bridge.
Which really leaves us with a big question to chew on, doesn't it?
What's that?
If AI gets really good at turning clear English instructions into working code, does the most valuable skill shift? Maybe it becomes less about mastering the specific syntax of C++ or Python.
And more about your ability to define a problem rigorously and unambiguously, so that even a machine or an AI can understand it perfectly.
Exactly. Is that the core skill for the future? Something to think about.